Hello, I'm Tobias Zier, and I'm a PhD student in the Computer Graphics group at Karlsruhe Institute of Technology. This talk will be about correlated Monte Carlo rendering techniques, such as metropolis light transport. Specifically, we look at how placement of correlated samples can be improved, using only easily available properties of light transport paths. While the title may seem awfully specific to Markov chain Monte Carlo, I hope this talk can bring you some new ideas for all kinds of correlated sampling techniques. In adaptive rendering approaches of correlated samples, when we find rarely sampled light transport paths, we typically need more similar paths in the surroundings to know what the respective pixels should look like. In what regions to look for such paths is a difficult question. In these renderings using previous techniques, we can see why this question matters. All of the shown techniques are using a mix of heuristic correlated sampling strategies. Thus, they hope to cover all the different kinds of steps that are needed to follow the respective distributions of light transport. However, we can see that their adaptivity is often limited in practice. Even for advanced techniques like manifold exploration, which is tailored to cover particularly difficult regions of transport paths, the right balance between all of the regions is not always quickly achieved. In our work, we set out with one of the most simple mutation strategies thinkable, using purely forward path sampling. For this strategy, we optimize the shape of proposal distributions to fit the distribution of transport paths, and we find that this alone can not only lead to more consistent results, but sometimes even outperforms previous, expectedly more robust techniques, such as using bidirectional path sampling. We conclude that choosing the right amount of correlation is extremely important for good results. Our approach draws on ideas introduced in manifold exploration by Jakob and Marschner, which allowed new types of path vertices to be mutated efficiently within the constraints imposed by specular refractions or refractions. Our approach also uses results from half-vector space light transport by Kaplanian et al., which, in contrast to manifold exploration, allows to mutate many constrained vertices at the same time. Also, it introduced the idea of projecting pixel footprints forward onto other vertices to determine good anisotropic distributions for correlated samples. A similar mechanic arises from our analyses, but without a need for a roughness-based distribution heuristic. More efforts towards good anisotropic proposal distributions have been made drawing from the Hamiltonian Monte Carlo framework. There, correlated samples are placed in accordance with the analytic solutions of impulse-based dynamic simulations within local transport distributions that are defined by second-order derivatives. As these derivatives are complex to compute, they are obtained by automatic differentiation. With a similar dynamics background, a recent work by Luan et al. Simplifies obtaining good adaptive proposal distributions in a way that requires only first-order derivatives. In this presentation, we will work towards even more simplicity and ultimately get rid of any actual derivatives. To understand how certain sample distributions cause variance, let us look at the types of light scattering that can occur along a light transport path. We observe that for deterministic light transport, so basically paths with only mirror or refraction interactions, we usually face much less of a problem with variance. There, already a standard path tracer tracing rays from the camera usually does a decent job. The variance we face in this case is basically due to aliasing. In non-deterministic transport, however, much more variance can be caused by the random scattering of light in arbitrary directions. Let us recap how variance arises. Monte Carlo integration constructs paths x from unit random variables u. The random vectors u are points in a unit hypercube, which is also called the primary sample space. With increasing number of samples, the average of resulting sample values f of u converges to the pixel brightness ij that we want to compute. The variance due to varying sample values is simply the integral of these sample values squared. What we are interested in is the potential deviation of pixel estimates from the correct result. It is quantified by relative variance. We can bound it by a simple expression, namely the quotient of the maximum sample value, so the range of sample values, divided by the correct result for the pixel we want to compute. Calculating these two quantities for the actual light transport, compared to what we would get for deterministic light transport, allows us to characterize the difference in resulting variances. Looking at the sample values for a forward path tracer, we find that their range is in fact not all that different for different types of scattering. Differing values of reflectivity are usually cancelled out by BSDF importance sampling successfully. If we look at the resulting pixel brightnesses, however, different distributions of sample values may of course lead to very different results. Therefore, this is the quantity that we will look into further to compare the relative variances. Let us first focus on a small subset of samples in the local environment of a single light transport path. We define this environment by a masking function g of u the function is 1 for the light transport path in the center and goes to 0 at the boundaries of the environment. If the environment is sufficiently small, there's actually a chance that we will have sufficient information to compute an integral value for the paths contained by it. Note that at each path vertex, we have random variables with known distributions corresponding to light scattered from different directions. With a simple convolution, we can determine contribution of each point on the light source to our local environment. The deterministic case is even easier, as there is no light scattering at any inner vertices. Then, we effectively just project the footprint of the camera pixel forward onto the light source. With this, we almost have all the information we need to get an understanding of the different relative variances. If you paid close attention, you will ask yourself how such integral values for small subsets of samples help us, with our ultimate goal to quantify the relative variance of all light transport within a pixel. With our local comparison, we effectively take a subset of transport paths away from all of the transport for experimentation. In this subset, we analyze what would happen if transport was deterministic, rather than what we find in the actual scene. The rest of the light transport outside our subset remains unchanged for our experiment. For a subset, we can compute the ratio of integral values. This ratio, tilde r, quantifies the quotient of experimental deterministic to actual light transport. If we combine the experimentation subset with the rest of light transport, we would obtain a different ratio r. Yet, we find that whenever in the subset there is more transport for the deterministic scenario, then the ratio for combined transport is in fact bounded by the subset ratio. Going back to variance estimation, remember our characterization of relative variance by the maximum range of sample values f hat and the pixel value ij. We can trivially replace the pixel value by the value for locally altered deterministic transport if we compensate by the ratio r. It then follows that the relative variance can also be bounded using the ratio within our local subsets tilde r. This characterization tells us that if deterministic light transport in a local environment would be much brighter than our actual light transport there, then the relative variance for the whole pixel might be equally higher in the worst case. We can immediately test the effectiveness of this variance bounding in a Firefly detection experiment. If we reweight every path inversely to the bounding ratio tilde r, we see that it suppresses Fireflies and bounds variance reliably. Note that this is already useful for adaptive sampling in itself whenever we want to identify difficult paths for additional exploration or guiding. We have run this test for many scenes, as can be seen in the supplementary materials of our paper. In all cases, the images come back smooth, removing the light transport that is potentially unreliable due to unpredictable light scattering. We can also use controlled pixel estimates to stratify Markov chain Monte Carlo rendering. If we multiply the splats of the chain by the estimates and compensate with an importance function that is altered accordingly, the results stay unbiased. As a consequence, reliable bright samples can be split directly. This allows the Markov chain to move on, guiding samples away from trivial bright light transport. Thus, we get a much higher effective sample count per pixel in all the darker areas of the image. This becomes visible in a false color visualization, counting the number of times that the Markov chain reached each pixel. In the unstratified case, most time is wasted on exploring the directly visible light sources. In the stratified case, the light sources do not get any more samples than their surroundings. Our approach can also improve results in less contrived scenes whenever we face a high dynamic range. For highly scattering materials, our variance estimation can be over-conservative. An easy additional improvement that we can make is to incorporate other variance reduction features that are already existent in a typical renderer. For example, in most renderers, a lot of effort is already put into controlling the variance of direct illumination, performing next event estimation with multiple importance sampling. With its controlled variance, we can effectively turn the penultimate vertex into a virtual light source. This allows us to decrease the number of vertices that go into our variance estimation, reducing over-conservative estimates. As we can see, the stratified Markov chain can equally quickly handle the bright light seen through the windows and the direct illumination, creating their glossy reflections. Comparing our stratification to previous work, our approach is farther away from perfect stratification than the previous multistage MLT. This is to be expected, as our approach is based on only local information that potentially leads to overly conservative estimates. In contrast, multistage MLT works by reusing final results of recursively refined image estimates. If the multiple stages are balanced correctly, and all intermediate images can be converged, multistage MLT can lead to very high quality stratification. In practice, however, multistage MLT can cause robustness issues. The typical correlation artifacts of MCMC methods become amplified when they also occur in the guide images of intermediate stages that did not fully converge. This leads to noticeable additional flickering. Our method uses only deterministic information to guide the Markov chain, therefore it does not introduce such issues. So finally, how do we use our previous observations to determine good regions for correlated samples? We begin by defining the region that we look for with a masking function g of u, which is 1 for the current seed path and goes to 0 for the boundaries. G of u defines where we will put our correlated samples. Our optimization goal for the region is the fast exploration of path space. This coincides with a minimization of correlation, which is good for temporal stability. To achieve this goal, we maximize the volume of the region in which we will place our correlated samples. Of course, we also need an optimization constraint that controls the quality of these samples and thus prevents our adaptive sampling to degenerate into completely independent sampling. Drawing from our previous ideas, we constrain the variance of the adaptive samples in such a way that it does not exceed a certain multiple of what we would expect if all light transport was deterministic within our sampled region. Thus, we can maximize our sampling region and minimize sample correlation while keeping the variance of resulting samples under control. In practice, we define our sampling regions as multivariate Gaussians centered around a current path x. Then, the optimization problem becomes a simple Karish-Kahn-Tucker system. We define the constrained optimization in terms of the variance bounding ratio tilde r introduced earlier. Additional inequalities arise from the fact that the primary sample space is bounded within the unit hypercube. The system is very easy to solve analytically, essentially by computing a Lagrange multiplier until all conditions are met. This usually takes very few tries. Sampling paths within the resulting regions can drastically improve temporal stability. Compared to other bidirectional methods, our simpler but more holistic algorithm can also lead to more consistent image quality. Finally, minimizing the correlation of proposal samples works towards filterability. Here, we simply apply density-based outlier reweighting to the splats of our algorithm. Like many filters, this technique was designed for independent, uncorrelated samples, therefore it works best for minimal correlation. I would like to conclude the talk with 2 more technical notes. So far, we simply assumed the availability of accurate path differentials. For any direction sampled, this would require the renderer to be differentiable with respect to the corresponding random variables. While this is feasible, we would like to avoid the added complexity in practice. In our first experiments, we instead used half-vector derivatives, treating projected half-vectors as if they were random variables. In accordance with microfacet theory, this turned out a good fit as well, leading to meaningful path differentials. However, for our purposes, we found that we can even eliminate derivatives entirely. We pretend that our geometry is tessellated into planar patches, which can be arbitrarily refined. A paper from 2007 and follow-up work on the construction of paneled buildings show that we could indeed construct such patches systematically. On our virtual linearized geometry, angle perturbations and positional perturbations are mostly preserved for both reflection and refraction, except for a few scaling factors. This allows us to construct useful approximate path differentials solely based on the solid angle PDFs of forward path sampling. All other terms visible in the formula are scalar density compression coefficients, which can be easily tracked during path construction. On a second technical note, it is not entirely obvious how to embed an effective path tracer in a metropolis light transport setting. In our paper, we describe how to make use of the reversible jump framework to efficiently construct many paths of different lengths simultaneously, mixing multiple techniques. Our approach should be generalizable to the embedding of other Monte Carlo techniques as well. Besides the path tracing large step, our rendering algorithm only has one other mutation strategy, which performs the adaptive path sampling that we discussed. I want to emphasize that the resulting rendering algorithm is surprisingly concise and simple. The path tracing large step requires minimal changes to a standard path tracer, and the adaptive small step merely keeps track of a few scalar quantities along the path. Both should be easy enough to implement off of these 2 listings as printed in the paper. With this, I would like to conclude my talk. We saw that anisotropic shape of proposal distributions matters. By minimizing correlation under variance constraints, we can get better robustness and improved stability. We also saw that certain kinds of variance estimation are feasible based on only local information of individual samples. We hope that this proves useful for other adaptive rendering techniques in the future. Finally, we found that controlled correlation in adaptive rendering improves filterability. We hope that further improvements can be made by coupling the amount of correlation with a suitable filter. This ends my talk. Thank you for your attention. You can find the full source code of the project online, and please feel free to contact me for any further questions or discussion.